Across the incomprehensible expanse of the universe, silence reigns. Not the silence of peace, but the profound, crushing quiet of distances so vast that even light, racing at 300,000 kilometers per second, takes millennia to cross the void between stars. In this darkness, death arrives in many forms. But not all endings announce themselves with fire. For generations, humanity has gazed upward and imagined stellar death as a spectacle, a violent eruption of light tearing through the cosmos, a supernova marking the final scream of a dying giant. These cosmic fireworks have become the signature of stellar mortality in our collective imagination. Brilliant, catastrophic, inevitable. The death throes of massive stars we believed would always illuminate the heavens, transforming a single point of light into a radiance that could outshine entire galaxies for weeks or months, before fading into memory. But the universe, as it so often does, has revealed a different truth. One far more unsettling. In the closing decades of the 20th century, astronomers began to notice something peculiar in their catalogs of dying stars. Red supergiants, bloated stellar behemoths approaching the end of their nuclear lives, were disappearing. Not in the expected flash of a supernova, but in silence. Telescopes that had tracked these massive stars for years recorded them dimming, faltering, and then nothing. Where there should have been an explosion powerful enough to forge the heavy elements that make up planets and life itself, there was only absence. A star that had burned for millions of years simply winked out, leaving behind a faint, ghostly remnant, or sometimes no trace at all. The confusion was immediate and profound. These weren't small stars, the kind destined to fade quietly into white dwarf obscurity. These were giants, massive enough that every model of stellar evolution demanded they end in a supernova. Yet the expected cosmic violence never arrived. Observational campaigns mounted to study these stellar deaths captured the final months of red supergiants growing dimmer, their spectral signatures shifting, their light becoming erratic. Then darkness. The telescopes still pointed at the same coordinates, recorded nothing but the empty backdrop of space. The first documented cases emerged from systematic surveys designed to catch supernova in neighboring galaxies. Astronomers compared images taken years apart, searching for the telltale brightening that signals a stellar explosion. Instead, they found the opposite. Stars that had been catalogued, measured, and monitored had vanished from subsequent observations. No explosion, no expanding shell of debris, no pulsar left behind as a cosmic lighthouse. Just gone. The implications settled over the astronomical community like a shadow. If massive stars could die without exploding, then everything about the final chapters of stellar evolution required reconsideration. The question emerged, quiet but insistent. What happens when a star dies without exploding? The answer, as data slowly accumulated over decades, pointed toward a transformation more profound than any supernova. These stars weren't simply fading away. They were collapsing inward, imploding under their own immense gravity with such totality that even the light of their death couldn't escape. In those final moments, as the core temperature soared beyond comprehension and matter compressed past all known limits, something else was being born. Something that devoured even the explosion itself. A failed supernova, astronomers realized, might be the most violent death of all. A stellar suicide so complete that it erases itself from existence, pulling its final breath of light down into an abyss from which nothing, not even the announcement of its own demise, can emerge. The universe, it seemed, had kept its darkest secret hidden in plain sight. In 2009, astronomers captured routine images of NGC 6946, a spiral galaxy lying 22 million light-years from Earth. Among the billions of stars scattered across its disk, one red supergiant burned with particular luminosity, a stellar giant catalogued as N6946BH1, massive enough to dwarf entire solar systems, bright enough to be tracked across the cosmic void. It was unremarkable only in that it fit perfectly within the expected trajectory of stellar evolution, a star approaching the end of its fusion cycle, destined to die in a supernova that would briefly outshine its host galaxy. But N6946BH1 had a different fate written into its core. Between 2009 and 2015, observational teams monitored the star as it entered its final phase. The expected moment approached, the instant when fusion would fail, when the core would collapse, when the star would detonate in a cascade of thermonuclear fury. Telescopes stood ready to capture the spectacle, to measure the light curve of another cosmic explosion, to add another data point to humanity's catalog of stellar deaths. The supernova never came. Instead, something far stranger unfolded in the darkness. N6946BH1 began to fade. Not suddenly, as if extinguished, but gradually, its visible light dimming while its infrared signature grew brighter, as though the star were pulling a veil across itself. For months, instruments tracked this peculiar transformation, watching as the massive star dimmed into obscurity. Then, in what astronomers would later describe with scientific understatement as optical disappearance, N6946BH1 vanished entirely from the visible spectrum. Where a supergiant 25 times the mass of the Sun had burned, there remained only silence and shadow. The shock rippled through the astrophysics community. A star millions of times larger than Earth, a fusion furnace that had burned for millions of years, had disappeared without the signature blast that should have announced its death across the cosmos. The implications were staggering. If N6946BH1 had failed to explode, then the standard model of stellar death required revision. That model had seemed so certain, so inevitable in its logic. When a massive star exhausts its fuel, fusion ceases. Without the outward pressure of radiation to counterbalance gravity, the core collapses in milliseconds, compressing matter to densities that defy comprehension. This collapse generates a shock wave, a rebound of energy as matter crashes inward and then rebounds outward, tearing through the star's outer layers in an explosion powerful enough to synthesize heavy elements and scatter them across light years of space. A supernova. The expected ending. But in the failed supernova, the script changes in the final act. Gravity, that patient and inexorable force, overpowers the rebound. The shock wave that should have torn the star apart stalls, trapped by the intense gravitational field of the collapsing core. The energy that should have exploded outward turns inward instead, feeding the collapse, accelerating it. The outer layers of the star, robbed of their explosive exit, fall inward after the core, adding their mass to the growing singularity at the center. The star doesn't explode. It folds inward, swallowing itself whole. An implosion rather than an explosion. A death marked not by the creation of light, but by its consumption. Yet the mystery deepens beyond mere observational anomaly. The question transforms from what happened to something more profound. Does the star die, or does it transform into something else entirely? The evidence suggests a process both gradual and catastrophic. In the months following N6946BH1's disappearance, sensitive instruments detected faint flickers in the infrared, brief pulses of energy, consistent with matter spiraling inward at relativistic speeds, heating to millions of degrees as it approached an event horizon. Gravitational wave detectors, though not yet sensitive enough to catch the signal definitively, hinted at the possibility of tremors in spacetime. Itself, the subtle vibrations that might accompany the birth of a black hole, through direct collapse rather than explosive rebound. The implications stretch beyond a single vanished star. Some theoretical physicists, analyzing the demographics of stellar death across observable galaxies, have begun to propose a startling possibility that the universe contains more silent deaths than violent ones. That for every supernova that lights up the cosmic darkness, another massive star may collapse directly into a black hole without fanfare, without light, without any announcement of the transformation taking place within its collapsing core. If true, this suggests that black holes, those enigmatic punctures in the fabric of spacetime, may be seeded not primarily by chaos and explosion, but by subtlety and silence. That the most extreme objects in the universe, gravitational wells so deep that not even light can escape, might form not from the debris of violent death, but from a quiet, inward folding that consumes the star entirely, leaving nothing behind but an invisible singularity and the faintest whisper of gravitational distortion. N6946BH. One's disappearance opened a door into this hidden realm of stellar mortality. But the star itself offers no answers from beyond its own event horizon. It has crossed a threshold from which no information can return, transformed from a massive, luminous giant into something that exists primarily as absence, a region of space where gravity has become so intense that it warps reality itself, the observation. Teams continue to monitor the coordinates where N6946BH1 once burned. The telescopes see nothing, but absence, they are learning, can be as revealing as presence. In the darkness where a star used to be, something new has been born, or perhaps something ancient has been unveiled. A fundamental process that has been occurring since the first massive stars died in the infant universe, hidden in plain sight by the very nature of their transformation. The star folded inward, and in doing so, it revealed that the universe's most violent deaths might also be its quietest dot in the computational chambers of astrophysics laboratories across the world. Supercomputers reconstruct what telescopes cannot see, the final moments of a star suffocating under its own gravity. These simulations, built from equations that govern matter at its most extreme, reveal a process that unfolds in fractions of a second, yet carries consequences that echo across cosmic time. A direct collapse black hole begins its existence in the core of a massive star where fusion has failed. Without the outward pressure of nuclear fire, gravity claims absolute dominion. The core implodes at nearly a quarter the speed of light, compressing stellar matter into densities that exceed atomic nuclei. In ordinary supernova, this collapse triggers a rebound, a shock wave that tears the star apart. But in direct collapse, something different occurs. The infalling material carries so much mass, so much gravitational potential, that the shock wave never escapes. It stalls within the collapsing envelope, trapped by the very gravity it was born from. The simulations track what happens next with mathematical precision. The outer layers of the star, robbed of their explosive exit, accelerate inward. Matter streams toward the core in a catastrophic avalanche, falling faster, compressing tighter, heating to temperatures where physics itself begins to blur. And then, in a moment both instantaneous and eternal, the event horizon ignites. This is the threshold beyond which causality breaks. The collapsing core compresses past the Schwarzschild radius, that critical boundary, where escape velocity exceeds the speed of light. The event horizon erupts into existence, expanding outward through the infalling matter like a sphere of absolute darkness consuming everything in its path. Light attempting to escape finds itself trapped in curved spacetime, forced into orbital trajectories that spiral inward. The star's final photons, the last electromagnetic testimony to its existence, curve back toward the singularity forming at the center. They vanish across the horizon, their energy added to the growing mass of the newborn black hole. The star has not exploded. It is transformed into absence itself, a region of space-time so warped that it becomes functionally disconnected from the observable universe. Yet the transformation does not go entirely unwitnessed. Humanity has built instruments sensitive enough to catch whispers from these silent depths. Tools that probe the cosmos through channels beyond visible light. The James Webb Space Telescope, orbiting beyond Earth's obscuring atmosphere, peers into the deep time of distant galaxies with infrared vision sharp enough to resolve individual massive stars. Its mission includes hunting for the telltale signature of vanishing supergiants, stars that fade from view across cosmic epochs, their disappearance marking the potential birth of direct collapse black holes in the early universe. By cataloging these stellar ghosts across different eras of cosmic history, astronomers hope to determine whether failed supernovae were more common in the universe's youth, when the first generation of massive stars died without the heavy elements that might have altered their final fates. Beneath mountain ranges and deep within ice sheets, neutrino detectors wait in darkness for particles that pass through the Earth as though it were vapor. These ghostly messengers, produced in the cores of collapsing stars, carry information from the moment of transformation itself. A supernova produces a burst of neutrinos powerful enough to be detected across the galaxy, a flood of particles announcing the core's collapse. But a failed supernova produces something different, a truncated burst, a neutrino signature that cuts off abruptly as the event horizon forms and severs all communication from within. Physicists pore over data streams, searching for these abbreviated signals that might indicate a star folding inward rather than exploding outward. Gravitational wave observatories add another layer of observation. Arrays of laser interferometers, separated by thousands of kilometers, monitor space-time itself for the ripples that accompany massive, accelerating objects. When a stellar core collapses beyond the point of no return, it should produce tremors in the fabric of reality, subtle distortions that propagate outward at the speed of light, carrying information about the mass spin and final configuration of the newborn black hole. The detectors listen continuously, waiting for the gravitational whisper of a star compressing past the boundaries of known physics. Yet, the mystery deepens when theory ventures beyond black holes into more exotic possibilities. Some models suggest that under specific conditions, a collapsing stellar core might not form a black hole at all, but instead stabilize into something stranger, a quark star, where matter has been compressed until protons and neutrons dissolve into their constituent quarks, creating a form of matter that exists nowhere else in the contemporary universe. Or perhaps a boson star, a hypothetical object held up not by nuclear forces, but by quantum pressure from exotic particles. A stellar remnant that would appear almost invisible, yet possess mass comparable to neutron stars. More speculative still are proposals, linking failed supernova to the universe's greatest mystery, dark matter. Some cosmologists theorize that primordial black holes form not from stellar collapse, but from density. Fluctuations in the early universe might account for a fraction of dark matter's gravitational influence. If massive stars in the infant cosmos collapsed directly into black holes without exploding, they might have seeded the universe with a hidden population of intermediate mass black holes that now shape galactic structure from the shadows, their gravity guiding the formation of galaxies, while remaining forever invisible. This leads to a profound question that resonates through observational astronomy. Are there entire galaxies built upon the quiet deaths of stars? Could the dark graveyards of failed supernova form a hidden scaffolding for cosmic architecture, their collective gravity acting as anchors around which visible matter gathers and luminous structures form? The universe may be shaped as much by what remains hidden as by what shines. The field of transient astronomy has shifted from passive observation to active pursuit. Networks of automated telescopes scan the sky nightly, comparing each image to those taken before, searching for stars that have vanished between observations. Astronomers race to catch a failed supernova in progress, to watch in real time as a massive star dims and folds inward, to capture the spectrum of its fading light, to coordinate observations across wavelengths and messengers, assembling a complete portrait of a star dying without shining, because somewhere in the cosmos, at this very moment, another massive star is reaching the end of its fusion cycle. Its core is beginning to collapse, and in the seconds or minutes that follow, it will either announce its death with light visible across the universe, or it will fold silently inward, crossing the threshold into darkness, adding one more invisible singularity to the population of black holes that haunt the spaces between stars. The birth of darkness, it turns out, happens more often than the explosions of light. And each time it does, the universe gains another region where space-time curves back upon itself, where matter and energy vanish from the cosmic ledger, where the laws of physics approach their breaking point, and perhaps, just perhaps, hint at something beyond. Humanity has always been drawn to spectacle. Throughout history, the collective imagination has equated endings with eruption, collapse with catastrophe, transformation with thunder. In the theater of the cosmos, supernovae have played the role that seemed most fitting for stellar death, brilliant, violent, impossible to ignore. These cosmic fireworks satisfy something fundamental in the human psyche, the belief that power must announce itself, that significance must be loud, that anything worthy of attention must demand to be seen. Yet the universe, in its patient instruction, teaches a different lesson. Not all power arrives with fanfare. Some of the most transformative events in the cosmos occur in silence so complete that they erase even the possibility of sound. The quiet deaths of stars, those failed supernovae that fold inward rather than explode outward, reshape the architecture of space-time without demanding recognition, without leaving visible scars, without offering the spectacle that human observers have come to expect from stellar mortality. These silent transformations create black holes not through rage, but through surrender. A star that has burned for millions of years, that has held itself against gravity through the constant violence of fusion, finally relents. The nuclear fire dies. Gravity, which has waited patiently at the threshold all along, claims what was always inevitable. The star does not fight this ending with an explosion. It yields to it, folding inward with a totality that borders on the mystical, allowing itself to be compressed beyond the point where matter retains meaning, where time flows forward in the conventional sense, where information can escape to inform the watching universe of what transpires within. What does it mean for something to vanish without leaving light? The question haunts physics and philosophy alike. A star is, at its essence, a beacon, an object defined by its luminosity, by the photons it hurls across the void to announce its existence to any observer capable of seeing. When a massive star collapses directly into a black hole, it transitions from this state of maximum visibility to one of absolute concealment. The light that once radiated from its surface curves back into the singularity. The electromagnetic signature that made it observable across light years of space terminates at the event horizon. The star becomes a region of space-time defined entirely by absence, by what it prevents rather than what it emits. This is not destruction in the conventional sense. Matter does not cease to exist. It transforms into something for which human language has no adequate descriptor. The atoms that once fused in the stellar core, the photons that once carried energy outward, the very space-time that once extended through the star's volume, all of this continues to exist, but in a configuration so alien to ordinary experience that observation becomes impossible. The event horizon is not a wall or a surface, but a threshold of causality itself, a boundary beyond which even the concept of inside loses coherence from an external perspective. There is a strange beauty in this impermanence, in the recognition that disappearance is not always annihilation but transition. The star does not end. It crosses into a state where its continued existence is fundamentally inaccessible to the universe it once inhabited. It becomes a memory encoded in curved spacetime, a gravitational echo of something that was but can no longer be directly witnessed, somewhere in a distant galaxy. At this very moment, a massive star is exhaling its final breath of fusion. Its core temperature drops below the threshold needed to sustain nuclear burning. Gravity tightens its grip. The star begins to collapse. There will be no fireworks, no explosion bright enough to outshine 100 billion stars, no expanding shell of debris to seed future generations of planets and life. Just a dimming, gradual, then sudden, as the event horizon forms and expands outward through the infalling matter, sealing away the star's final moments from all external observation. A doorway opens in the fabric of spacetime. Not a doorway to another place, but to another state of being entirely. On one side, matter as the universe has known it, organized into atoms and photons, subject to thermodynamics and electromagnetic force. On the other side, a singularity where density approaches infinity, where time becomes space-like and space becomes time-like, where matter forgets it was ever matter and becomes pure gravitational curvature. The transition takes milliseconds. The consequences are eternal. The black hole that forms will persist for eons beyond measure, slowly evaporating through Hawking radiation over timescales that dwarf the current age of the universe. It will wander through the galaxy, occasionally consuming gas or capturing stellar companions, growing incrementally larger with each meal. It will merge with other black holes in collisions that ring spacetime like a struck bell, producing gravitational waves that carry information about these unions to distant observers. It will participate in the long, slow heat death of the cosmos, one of countless singularities that mark where massive stars once surrendered to gravity's patient call. But in this moment of formation, in the instant when the event horizon ignites and a star vanishes from the observable universe, there is only quiet. The cosmos does not announce this transformation with light or sound. There is no cosmic fanfare, no electromagnetic signature visible across the universe to mark the birth of something so profound. The universe does not always shout its most important moments. Sometimes, perhaps more often, than humanity has yet learned to recognize, it whispers the end of a star and begins the story of a black hole in silence so complete that only the most sensitive instruments can catch the faintest echo of what has transpired. And in that whisper, in that gentle folding of matter into darkness, the cosmos reveals a truth that spectacle often obscures, that power need not be loud, that transformation need not be visible, and that the most mysterious objects in existence are born not from violence, but from the quiet surrender of stars that have finally reached the end of their long journey through time. Death is silent, but the implications resonate across eternity.